Welcome to my hyperelastic materials project for 56900. We're going to start with some introduction and basic background information, tell why we're doing the experiment, talk about the model and the geometry and the equations that it runs off of, model and simulate it, and discuss the results. Hyperelastic materials are very strange. After they deform, they come back to their original position. The most common example that you'd think of is rubber. The goal is to analyze how something acts during a hyperelastic deformation, and ANSYS will run the simulation and show what a real-life model should look like. So, following some tutorials I found online, most of them pulled a test coupon through some fixed structures. A 2D model saves a lot of time, but a 3D model can be done. ANSYS can import a lot of different geometries from different files, but I had a little bit of trouble with this. So the shown geometry will be set up and analyzed. The goal is this test coupon gets pulled through the supports, and the larger circle at the end will deform. The governing equations can be seen from the Mooney-Rivlin 5-parameter equation. There are several other ones that Mooney-Rivlin developed, and there's a few other people that developed some equations, but Mooney-Rivlin is the most common and usually the most accurate. Interestingly, the Ogden model can account for the most deformation. So if you saw the equation, it had several material constants. These were developed from test data, and ANSYS was able to run a simulation and match this data to an equation. The simulation we will be doing is static structural. It's close enough to static as it'll be slowly pulled through the object. If it was pulled fast, you'd have to do a transient response. The default for ANSYS is steel, but that's not hyperelastic at all. So we have to go into the engineering data, remove steel from the list, add a hyperelastic material and some other structural material. So you can use steel if you want for the outside structure. So first we'll double click on engineering data, a new window will pop up. We'll be able to click on engineering data sources to find hyperelastic materials. We'll click on hyperelastic and you'll be able to find the elastomer sample, and the plus sign adds it to your list of materials you can choose from. You can hit the engineering data button again to exit the material selection and go back. We can find some test data for the uniaxial test. You can drag and drop the test data into the model type. As seen here, you drag Mooney-Rivlin 5-parameter onto uniaxial test data. You'll have to expand the Mooney-Rivlin 5-parameter, go to curve fitting, solve curve fit, copy calculated values to property. This will fill in all your yellow boxes with the equation values, your C values. We'll also need to add a material for the rigid support, but these are already pretty clearly defined. So you just go in, pick an engineering data, hit the plus for any generic, pick something that's strong that will not deform. We plan on doing a two-dimensional simulation to save time. So go to Geometry, Options, or Properties, select Two-Dimensional Model, and then import Geometry. Or New Design Modeler. I had more luck with creating designs directly in ANSYS, so the New Design Modeler may be the best way to go. Hit Generate to load your structure after it's been created, or use the Sketch tab to create a two-dimensional surface, and then use the Concept tab to find Create Surface from Sketch. The boundary conditions are set through the static structural section. First, we'll define all the properties by clicking on each individual section. As you can see in the picture, assigned material, click the material that you want. The test coupon will be elastic, and the other two will be your support structure. Contact is done under the Connections tab. We will insert a manual contact region, select the outside of the coupons and the outside of the rigid supports. To make it slightly more realistic, we add a frictional contact type, and we used a coefficient of friction of 0.14. As you can see, when you're setting it up, it shows you which the target surface and the contact surface. We change a few settings to help our analysis look a little better. We change the formulation type to pure penalty through the drop-down menu. We change the normal stiffness to manual and to 0.1, update each iteration. The pinball radius will depend on the size of your geometry. For the geometry I used a pinball radius of 2 millimeters. For mesh, we go to Mesh, Insert, Refinement, and then we can select all three surfaces under the Add Geometry tab and apply. Then we'll manually click on each surface and generate mesh. So you have to click on each one separately, generate mesh, and then you can click the Mesh tab to see what your result looks like. Under the static structural option, we will have the test coupon displace along the x-axis for 40 millimeters. The length just has to be enough that it passes completely through the smallest cross-sectional area. The two supports have to be fixed, and I fixed them at the very top and the very bottom. Setting up the output. The analysis will determine how long the simulation takes. The more steps, the more accurate, but the more time. Large deflections definitely needs to be on because we're using hyperelastic materials. The output nodal forces to yes helps it be a little more accurate. We want to look at the deformation. So under the output solutions, we go to Insert Deformation, Insert Strain, and Insert Stress. The default settings are pretty good, so we don't have to change much here. After it's done, we can click on the Graph tab that will appear in the bottom middle, and you can run this and it'll go through, increase the time and show you the different settings. Unfortunately, my first simulation did not work out very well and the material just passed through. This may have been from how I imported the Creo files, and it may have worked better if I had directly used ANSYS. So the first time I ever did this, I tried to make it a little more interesting for myself, and I had trouble finding two-dimensional options, so I tried to make a jellyfish pass through something else. It didn't work, it just teleported through, so I tried some more stuff. Thanks to a friend's suggestion, I was able to make a file in ANSYS Sketch and use the concept create surface. So I decided to model Mario's shoe jumping on a Goomba. It was amusing, and as you can see, the material deformed a lot. The polyethylene support did not deform at all, and the hyperelastic deformed very rapidly. In the next slide, you'll see the stress, and the stress was very small throughout the whole time. So have fun, try to make your own example and see what you can find out about hyperelastic materials. Most of the properties will be the same, but with different geometries you have to change the pinball radius. Here's some of the sources I used. There were 2 YouTube videos that were very helpful, and 3 other sources that helped me get a background for hyperelastic materials and how they react.